you guys, we're recording. Okay, in our beach board media gallery. There's 2 videos, 2 chapter 6 videos. So I'm going to say, please watch them. All right. And a student just got through telling me that they really get a lot out of the videos. I know that you could go in. So obviously you can go back into our team site and look at old videos. To a certain point, I think they only last for 19 days. And man, I've been forgetting to go and back up the other ones. Hopefully they haven't passed chapter 4. I think I haven't put into the into YouTube. But these, so I put these in media gallery, and they're not on YouTube. So this is Beachboard Media Gallery, right? Which is, for those that aren't familiar, so our course home, right? You probably should get a page similar to what I get here. You go to content. Oh, not even go to content. Go to media. You don't even have to go to content. Just, there's a tab called media, and since I'm an instructor, well, you guys might have both 2 options too, but you go to course gallery. And in course gallery, you'll see the videos, right? So hopefully for chapter 5, you saw these 3 videos, because they help a lot with the homework. I just added 2 more. Chapter 6, a part 1 and a part 2, and then I added a chapter 4 one just because I had it in there, and maybe to help you. I think this one might be in YouTube, but I'm not sure. Maybe it's not. So just to help with the exam, because we have an exam in 2 weeks, right? So it's going to be on chapters 4, 5, and 6. So that's how you get to the media gallery. Okay, then we got exam 2 coming up on November 5th. So far, so good. We're good with that date. November 5th. It's going to cover chapters 4, 5, and 6. Okay. All right. So we're 2 weeks away. I posted homework number 6 on chapter 6, and it's due in 1 week from today. So it's October 29th. Right. So I have a bunch of them. I'm sorry that I haven't been able to grade them. I need to just do it. Can't stop, but I gotta stop finding excuses. But I had a rough week, as you knew, especially on the weekend. But I should be able the weekend to free up. Though I'm having work done on my house, and I've never had this kind of work done, where you have contractors coming in and out, and they're cool. They're nice people to work with and all that. And I'm very grateful that they're working hard, and happy that the weather's cool, because they have to do a lot of digging in my backyard. And I have a garage that has an addition that was not permitted, and so I need to have it permitted, and just for the safety of the of whoever stays back there. And it's uh,
Professor,
it's a pain. Yeah.
I have a quick question, man.
Yeah.
Sorry, I don't mean to get
No
off
problem.
topic
No,
too
no,
quick.
I'm good.
Real quick, you said it was not permitted. I actually have the same issue, man. Since I'm like a starving student, right? Like I had to build my own spot here. Like I can't afford rent, so I had to drop like 15 grand on this place.
Really?
Converted my mom's garage into a 1 bedroom apartment. How much did it cost you in fees and stuff for that? Like, was it expensive?
So, did you have yours permitted, or
Not
just
permitted yet. I
okay?
did it the
Yeah,
non-permitted way right now.
no. So that's my my garage is my daughter's staying there, And there was a, but see, the thing is, I didn't convert it. It was already when I bought the house. It was part of the garage was already like a room with a bathroom. It was
Oh, okay.
just ugly. You know, it was like it's probably hadn't been opened in like 30 years. It was really old.
Oh, wow.
Yeah, just so I converted. I put in maybe $2,000 to $3,000 just putting in like new toilets, new tub, new, that kind of stuff. I
It's
didn't put,
actually not bad. It's actually
yeah.
not bad, considering.
But to get it permitted, that's the other thing. It just depends.
Ooh.
Is it is it just the garage or is it like is there an addition?
No, it's a 480 square foot garage. I did everything from the plumbing, the electricity, nothing was here. Me and my dad did everything for the
Really?
past 6 months. Yeah, completely brand new everything.
Wow. Did you went out to the sewer line and all that?
Everything. Yep.
That's cool.
Everything.
You know
Electric,
what?
gas, everything.
As long as it's within the garage, it's probably not that much. I mean, the fees and everything, it's like the city, the just to start the permit, $600. And then they charge you to pull the permit. It's gonna be like $1,500, and but like most, well, no, like $2,000, but half of it you get back. It's like for a dumping fee. Like they got to make sure that you try to recycle stuff,
Okay.
and that's if you, but you already did everything, right? So you don't even have that. You'll get that feedback. So maybe
Yeah.
you'll be out of pocket for the city, maybe about $2,000.
So it's not like 15 grand, right?
No, the only
Okay,
thing
good, good, good. Cool.
it's here's the thing though, it's got to have been done right. That's where like, did you put the proper header at the openings, right?
Everything.
Yeah.
Yep.
So
My dad's
was
a
all that.
contractor. Yep.
So that's cool. So they'll check it out. They'll have an inspector and they might say, hey, you gotta put a bigger header over that opening, or you didn't put a bracing there. But that's kind of stuff you can do. Um, Aside from that, my biggest problem was that there was an addition. And for everyone waiting for, I'm sorry guys, but there was an addition and it wasn't raised. So it's on like flat on a slab right on the ground. That's the level with my yard. So they were saying, how does, and water did used to get in, but I just like sealed it really well. But they told me I have to grade my yard and I have to put like a French drain. I got to do all this kind of crazy stuff. And so my problem is because it wasn't done well. And then when they framed it, whoever framed it was like, man, there's no way will it resist an earthquake. It was like it wasn't framed properly. So I had to redo a bunch of stuff. So in your case, as long as you guys, trust your work, that it's, and you can go online, you can look for Long Beach or wherever your city is, ADU, accessory dwelling unit, and you can look. They'll have drawings of like how framing should be and all that. And as long as you did it right, I mean, you shouldn't have to pay hardly anything. If just in fees, it's only, yeah, maybe $2,000. And the good news is then you add square footage to your house, and your mom now has a more valuable house, and you can claim that bathroom if in case you did sell, and then you're gonna get your own address, right? That's my daughter's gonna get her own address.
No, it's
Um,
it's the same address, but it's all good. It works out.
yeah, but I mean, if you do a ADU conversion, if you get it permitted, you can have your own address, like apartment A, right? It's your.
Oh, that's pretty
And
dope. Yeah.
yeah, and
It's cheaper than paying rent, to be honest.
yeah, that's crazy. You got to
Yeah.
do that nowadays. Yeah,
Yeah. It's the only way to survive, to be honest. Yeah.
yeah.
But thanks,
No,
Professor. Appreciate it,
yeah.
man.
Oh, you're welcome. Welcome. Yeah, thanks for telling me, because yeah, so I'm in the middle of that, and this is a lot of hassle, but I mean, we're getting it done. So all right, so I posted the homework, and let's get started. All right. So no other questions. I'm going to get started on chapter 6. We're recording, so you don't have to worry about asking me to record, but I don't mind if you do ask me. Um, all right, chapter 6. So we're talking about the second law. All right, and the best way to start this is to go to get a snapshot from our PowerPoint slides. So last time I talked about thermal energy reservoirs. So in case you missed that, go to the recording from the last lecture. I just briefly talked. We talked about, now I'm going to talk about heat engines. What's a heat engine? Well, we talked about what a heat engine is not, right? We talked about how if you put a propeller in water, then if you spin the propeller, then you'll create, through the friction of the propeller, you'll heat up the water, and water heat will come out the side. However, it's not reversible. So in general, anything heat transfer is not reversible in general. In other words, when you lose heat, you can't put it back in without putting work, obviously. Right? I mean, if your cup of coffee, put the cup of coffee on the table, it's nice and hot from Starbucks. You forget about it, come back, it's cold, right? You obviously can't just tell the heat to go back in, right? You'll have to. You could reheat it, but you put it in the microwave. You're putting work into the cup of coffee to get it to. So and that's what I mean by reversible. You can't just flip a knob and then say, okay, heat, go back into the cup. Once you lose it, it's not reversible. That's the way heat in general is not reversible, and this is an example of it. If the water that I just had the propeller in, if I heat the water in, the propeller is not going to spin. I can't get shaft work out. So that's. But let's go into specifics here. Let's talk about a heat engine that we all know. That it's called the steam power plant. At least we know parts of it. We know the turbine part. We've talked about. So let's go ahead and paste this over here. My lecture notes. Okay. Excuse me. I'm sorry. I had a cough and I have to. When the weather changes, I start to get like like allergies and stuff, and I kind of have a small cough. All right. So second law. This is a steam power plant. And in chapter 5, you saw a little bit of that from the standpoint of the turbine. I'm not sure if we cover the boiler, but this is what there's the four components here. There's let's start with the pump. We pump liquid up to the boiler. The boiler, we receive energy from a source. Typically, that's natural gas, some natural gas burners or something. Bring it up to some superheated vapor, send it down. It actually through vapor, just through vapor pressure, it actually comes down. You don't have to pump it to the turbine. And then the turbine, it comes out, it's high pressure, high velocity. Well, it's actually mostly high pressure steam and high velocity, I guess. And then comes out and spins the impeller or the stator and the impeller of the turbine. And you get energy out this way in the form of work, shaft work. And then the steam still has some energy and comes out this way to a condenser. And then you have to extract the energy, the heat in the condenser so you can get the water to condense. And that's when the water condenses, it flows to the pump, and then the pump basically pumps it back to the boiler. So you can't pump gas or vapor. You have to pump only liquid. So you have to basically pull the heat out get to the point where you can just condense the liquid, and then it goes back to the pump. To get the pump to operate, you have to put work in, and then it completes the cycle. It goes back and around and around and around. This is your steam power plant. They're just steady state, like we talked about just in chapter 5. Everything was steady state. It means once you get it going, it just keeps going, right? As long as you provide energy, as long as you can dump power into the pull heat out somehow with a condenser or a heat exchanger, then it'll keep going. It'll keep servicing, giving you service, giving you electricity, giving whatever you have here on the side. All right, so the components here, again, there's the QN. We also call that QH because you're getting energy from a high temperature source, or TH. The heat that we pull out, we also call QL because you're pulling energy into a low temperature sink. So usually this is your environment, the atmosphere, right? If you had a car, right? Car works on the same principle, right? So your heat engine, let's go ahead and start putting it. So we're going to represent in general just any heat engine with this circle. Right. And if this is a steam turbine, a steam power plant heat engine, then it would be this representation. You can even draw it in here, like in small, like you have a boiler, and then you have a turbine like this, and you have a compressor and a pump, right? So sorry about it, really, I got to put a really shoddy turbine there. All right, so if this is a heat engine, and heat engines have work coming out of them, right? We'll call that, we're going to call this just work net out, and I'll tell you why. Because one thing so work net out is, I didn't really describe what work net out is. For the steam power plant, there's two work that you see here, right? There's work out and work in. So it's basically it's just work out minus work in. Okay. And then there's another thing that work you can represent work net out as well as QH minus QL. So if you know how much heat is going into your boiler, or how much heat you're using to heat up the steam, that would be QH. And you know how much heat you're throwing away, if you subtract the two, that's going to be equal to your work net out, which is, it's not the shaft work, it's not the work that comes out of the turbine, it's the shaft work minus the pump work. But usually the shaft work is, the pump is only a small percentage, maybe a percent. 1% of the energy that you generate at the turbine goes into pumping, so it's very small. So let's go ahead and continue with our heat engine here. So I'm going to go ahead and draw. Oh, so we have heat coming into the, and I'm going to do what I'm going to do is I'm going to draw. This is just a high temperature reservoir, TH. Again, high temperature reservoir is that squiggly line. It's the whatever the source, whether it's natural gas or whatever, and then I'm putting QH into the heat engine. And I am extracting, so the arrows point the same way, a smaller amount of heat. As you can tell by the thinner arrow, I'll color that blue. So it's a smaller amount of heat I'm sending out to a low temperature reservoir, which usually it's like the atmosphere. Nowadays, so there's if you guys around campus, right? If you guys ever go down, you take, like, just say you want to go to PCH. So on the corner of is it, so from the campus you go on Studebaker going south towards the ocean. You take Studebaker down, and that's actually Studebaker runs east-west, right? So take Studebaker east towards Los Alamitos to Seal Beach, right? Take Studebaker that way, and you're going to run across a power plant, right? It's the AES power plant, and it's on your left-hand side as you're going. It's on the corner of Studebaker and Second, right? So you make a right on Second, takes you to the ocean. So there, they just converted their power plant, because I was involved years ago, about 4 years ago, 5 years ago. I was part of a community commission. We were in the community. We sat on a board, and they were talking about converting the power plant to making it better, like higher efficiency, higher power. And what they were doing is they used to throw water away in the, they used to have they used to dump energy into the river, right? Because there's, if you know the AES, there's a bunch of rivers down there that go, they feed like a, what do they call that? I forgot the, like a, it's like a swampy area, wetlands. They call it a wetlands. So they stopped doing that, and now they're going air. So they put in air cooled. So so now they're putting the heat into the atmosphere, right? So that could be their, but it's the assumption it's low temperature, and it is much. It's even in a hot summer day, if it's 100 degrees, the temperature of the boiler is like 1,000 degrees or higher, right? So it's much lower temperature atmosphere than the temperature of the boiler, right? So this is our heat engine. These are the three parts that are required for a heat engine: is that you get work out, and that you pull energy from a hot a hot uh, a hot temperature source. I'll just call it source, and you throw energy. You dump energy into a sink. This is, in this case, a low temperature sink, and this would be QL. Right? So it turns out, so I want to show you what this means here. How did we come up with that equation here that I just put a check mark? Work net out is equal to QH minus QL. So I'm going to show you by dropping a box. I'm going to drop a control volume around my heat engine. And I'm going to do an energy balance there. So for goodness sake. Okay, here we go. So I'm going to go ahead and write this in orange here. So I'm going to say do a first law energy balance here. I'll do it down here. E in is equal to E out. This is of the yellow box that I'm talking about. All right, so let's go ahead and expand this down a little bit. All right, so what's coming in? What's coming into my yellow box, right? So what's coming in is I have QH coming in. So I have QH, and that's the only thing coming in. So what's coming out? I have work net out, and then I have QL. So if I go ahead and solve for work net out, if I solve for work net out, I have, what do I have? Work net out is equal to QH minus QL, which is exactly what I wrote here, right? So this is we're talking about the second law of thermodynamics, but I just used the first law to be able to give us some information about heat engines, okay? So this is what a heat engine is. And there's different types. Your car is a heat engine if it runs on gasoline. If it runs on batteries, it's not a heat engine. It's an electric motor with wheels, and that's treated differently. That's just basically, it's like your remote control car with little batteries in it. It's not a heat engine. You got the energy for those batteries probably from fossil fuels. I mean, I suppose you could get the energy from solar, but 99% of the energy, this depends where you're at, is going to be fossil fuel. If our electric grid is mostly fossil fuel, So I mean, there's some cities have higher percentages, or some states maybe 20% at the highest that it's produced by solar panels or some kind of a solar power plant. All right, so this is a heat engine, and let's talk about efficiency. So the efficiency of a heat engine, thermal efficiency. You guys remember the little eta symbol that we have? Usually you got, it's usually work net out over Q. What goes into the yellow box? It's QH, right? All right, so and we know that work net out is equal to QH minus QL. So I'm going to put, yeah. So divided by QH. And this is important. Whenever you do an efficiency, it's important where you got the work net out. So if this was electric, if this was work net electric, then you can't use this symbol. This is it's no longer an efficiency. So your work out and your energy out and your energy, or let me say your work out net out and your energy in, or QH in, they have to be thermal, which means they're hot, like they're produced through some kind of a high temperature, low temperature situation. So it's apples to apples. So you have an apple here, right? Divided by an apple here, right? So apple and apple, right? So you can't have an orange divided by a banana divided by an apple, right? Now I'm going to explain why some people will confuse coefficient of performance with thermal with efficiency. This is an efficiency, and if we get a chance, I didn't get the lecture at the last meeting, so might have to wait till the next lecture. Okay, so that's your thermal efficiency. What else can I say about that? Oh yeah, this is also equal to. You can divide top and bottom. You divide through QH, and you get QL minus over QH as your efficiency. Okay. All right, that covers efficiency. Good. All right. So can we save? Let's put the spotlight on this guy here, on QL. Maybe I got to type this out. Can we? Yeah, say QL. I can QL. Do we have to throw it away? Can we save it? Or can we convert it? Or can we, here's a better word. Can we add it to WorkNet out? All right, so the answer is no. So it's, no, we can't. That's the second law. It's part of the second law requirement. What does that mean? Well, let's look at this QL here. The QL for the power plant, for the steam power plant, is there. Remember, I told you why we needed to get rid of it, right? We need to get it out. It's so we can condense. Water comes here, comes down. This isn't really. This is what comes out of the turbine is, it can be anything from. It can be anything from superheated vapor. Hold on. It can be superheated vapor, or it can be saturated vapor, a mixture, or a saturated liquid. It could be any of these. So regardless of what they are, we need, in order to convert it to at the very least saturated liquid, or a liquid. Usually we want to subcool it. We want to bring it down. We don't want to send vapor to the pump. First, the pump won't work if there's vapor in there, any vapor bubbles. So if you ever had to bleed your own brakes, so if you have an old car, in college, I had a 1969 Volkswagen convertible that I loved dearly. I wish I would have kept. I would frequently had to bleed my brakes. I'd be hitting the brakes. All of a sudden, my brake pedal felt like soft, right? Like I'd have to push it further down in order to get the car to stop, or pump it. That's why you get the pump the brakes. Euphemism when you tell someone like, "Hey, hold on, slow down, pump the brakes." Um, it's because you have to literally have to pump the brakes in order to stop. So the problem is when that happens in an old car is there's vapor getting into your line or air, and you have to bleed. It's called bleeding the brakes. You have to get the air out of the pump, and you do that by pressurizing the pump with get someone inside your car and pump it a bunch of times, get a lot of pressure in there, and then there's a bleeding valve at the pump. You just open it and you hear like a right, and then you do like 5 or 6 times until you only get liquid coming out of that little valve, and then you backfill it with. I remember, man, it was like yesterday. I haven't had to bleed my brakes since I was, when I graduated from college. Right, first thing I did is buy a car, and that was the last time I ever had to work on my car. I loved working on my car, and you know, it's just, I don't do it anymore because all my cars are computers and all that. So anyway, QL, can we save it? And I told you that we needed to condense the liquid. And then what can we do with it? Can we feed it to can we somehow convert it to work and feed it to the workout of the turbine? And the answer is still no, right? So, because it's not that much heat, it's all you can really do with it is maybe you can send it to, instead of sending it to the atmosphere or to a lake, if you have a facility nearby, right? In a cold area, you can heat during the winter. You can use some of that heat, run it through heat exchangers and use it or you can heat up some water and run that through some pipes and maybe heat up your facility. And therefore it saves you cost, right? Having to use gas or electricity to heat up your building. But it's too low level heat. It's a too low of a temperature, too low level heat to feed it back to the turbine. So you lose it. You have to throw it away. There's a certain amount. In chapter 7 we'll be able to calculate that. What's the minimum amount of heat that I need to be able to throw away? Actually, we're gonna do it in chapter 6. Okay. So the answer is no, we cannot save it. Now let's get into a fun part here. So I'm gonna say a new, in case we want to go back to that. Um, let's go back to the second law. Second law of thermodynamics. All right. So these laws, this law and the first law. So there's the first law. So these laws are laws of physics, right? These are they're not the laws of physics. They're just part of the laws of the physics. So by violating them, you violate the laws of physics. So you can't violate them. So violating. Right. So I'm going to show you some examples of violating the laws of physics, or any of these laws. So got my heat engine. So let's just say that someone came to you. You're either a graduate student. I mean, you're ready to graduate, or or you're graduated, and you're telling people, hey, I'm an engineer. I'm a mechanical engineer, and just someone says, oh, good. There's a lot of people out there, a lot of inventors that don't have proper, or they're not trained in engineering or physics, and so they'll assume things, right? So for example, they say, hey, I got this engine, all right, and what I do is I put I created this engine, or I have this idea for an engine, and what I'm going to do is I'm going to, I have fuel, so I'm going to put fuel in it, all right, and then I'm going to put, and I'll give you an idea how much energy I'm going to put into it. So I'm going to put or just say I have this engine or engine concept. I'm going to put 100 kilowatts in here, right? And then I'm going to extract from it. I can extract I'm going to extract 100 kilowatts. Oops, sorry. So I'm going to, in terms of work. So this is what's going to lead to my 100 kilowatts is, what is that? It's 746 watts. So it's 0.7 watts or kilowatts, 0.7 kilowatts per horsepower. So this is greater than 100 horsepower, right? This is, not 200 horsepower, but somewhere up there in the upper hundreds horsepower. So it's a small car, it's not a big beefy car. But they say, hey, I'm getting gas. I'm converting 100 kilowatts of gas into 100 kilowatts of so it's 100% efficient. Surprisingly, this does not violate. So this passes the first law. All right, it passes. All right, because you have, remember the first law, assuming this is a steady state, E in is equal to E out. Right, and that's what we got here, right? We do have 100 coming in and 100 coming out. So where is the violation, right? There is no violation. All right. Now, so I passed the first law of thermodynamics, but I violate this. So this violates second law because I don't have this guy here. I don't have this going to I'm not throwing away energy. I have to discard energy, and there has to be a QL here. I just can't have a QH, right? Obviously this is my QH. I need to have a QL, and I don't have one, right? I can't have any because it's the first. Then it would violate the first law, right? If I say, okay, yeah, I'll give you QH, I'll give you QH or QL. QL is equal to 10 kilowatts, right? Well, then I violated it, right? Because I have 100 coming in, and I have 10 coming out. I should have 90 of work here left for work, but I'm claiming 100, so therefore I'm violating the first law. But this violates the second law because of that, because I'm not throwing away energy. And the law, the specific law is called the Kelvin-Planck statement.
Professor, you're saying that the second law is that you have to exhaust some sort of energy
Yes.
through heat?
Yes, you have
Okay.
to. So imagine your car. So one way I can get rid of the heat. So I plug your radiator, right? Just say I just surround it with insulation. I prevent your gas car, assuming you have a gas car.
Yeah.
I plug the radiator. Will it run? And it won't. It won't run. It might run a little bit, but not long. Or putting another way of putting this one's a little different, but the exhaust pipe, right? You're putting a banana or an apple or something, plugging that pipe. That's also that's part of your heat exhaust, and it'll stop running. Your engine will overheat, and you'll just
Okay.
Well, actually, for plugging the pipe, you'll probably get back pressure, and it'll prevent your gas from igniting, and you'll just putter out. But yeah, you have to throw away heat, and this is dictated by the Kelvin the Kelvin-Planck statement, which says the following. Let me see. I don't know it verbatim, but it says it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So it's basically saying what I just drew there. it's saying single, right? So it is. Let me go back to my pen here. Make sure I got the right thickness. All right. So it says from a single reservoir, and that's what I did. I didn't throw another reservoir down here. If I would have done this and had a little bit of heat leaking out, then I probably wouldn't have violated the second. I mean, this is an outright violation of the second law. And I almost did this on a patent, right? So I have a patent on. It's kind of similar to it's a Rankine cycle. It's very similar. We'll talk about that in the Rankine cycle in chapter 10. But it's very similar to the steam power plant. The steam power plants are a Rankine cycle, basically a boiler, turbine, condenser, pump. And I have a special Rankine cycle machine that has heat is not traditionally thrown away like this. So I neglected my first. I had just put the drawing together, and I sent it. I was just about to send it to the patent office, and I had to stop myself. And I said, "Oh man, I don't have energy coming out of and getting thrown away into a low temperature reservoir." And they would have sent the patent office would have sent it right back to me and said they would have said this on it. Um, actually, what would they? Let's see. Is that what they would have said? Let me see. I'm trying to find the exact. They would have said no. Not that. They would have said. It would have said you have a perpetual motion machine and it violates the second law of thermodynamics. They would have just stamped it like this, bam, and sent it back to me. But in reality, my concept had heat coming out. I just needed to diagram it that way to show it. I just didn't. I just neglected to put the arrow. So anyway, this means perpetual motion machine violates the second law. Perpetual motion means you're getting something for nothing. You're just um, by us even claiming it, we're at 100 kilowatts that we're converting from heat to work. Anyway, this is what it would have came back with. Now let me draw another. Speaking of perpetual motion, so let's talk about that machine. So a more clear perpetual motion machine would be to draw something like the steam turbine that we had. So let's do that. We have, come on. We have a boiler, goes into a turbine. From there we have work net out. And then the turbine then comes to a compressor, that's condenser. And then from the condenser, a pump back to the boiler. All right, so everything is cool. Nothing, I haven't given you any numbers yet, so there's nothing that could have violated yet. All right, so it's going, clockwise and all that. So now what we said is, all right, let's go ahead and say, hey, this pump works. Why don't we just put a shaft that connects the turbine with the pump? In other words, and that's fine. You can do that. You can actually run your pump with a shaft that takes, some of your energy in terms of work shaft out of subtracts the work out a little bit and it sends it to the pump. That's totally fine. You can do that. And then you say, okay, well, actually, let me do something here. I need to move this. I'll move it down here. And then you say, all right, well, let's connect a generator, right? So this is my generator. And for my generator, I'm going to have my power, right? That comes out in terms of work electric. And I'm going to have a positive and a negative. But then I'm going to say, well, all right, let's go ahead and what if I can connect the wire from my positive and then send it to my boiler and put a resistance heater, and then connect it there and connect it here. So what I'm doing is I'm transferring heat not from an outside source but from an inside source to the boiler there, and then I'm getting a net. I'll do this in orange. I'm getting a net work out. All right. So do you understand what I'm doing? So I grabbed electricity from the generator. I'm feeding it to the boiler through a resistive heater, heating the boiler, and then the process continues, right? We got, steam comes out this way, goes through my turbine, comes out that way, goes through the condenser. Here's the thing. I could still throw away energy. So I can throw away energy this way, QL. And so that is my energy, that's my reservoir. So this violates actually two laws. This violates the first law and the second law. So let me tell you why it violates the first law. Let's draw a control volume. So we know that what's crossing my control volume, well, we have this arrow going out, right? That's crossing my control volume. And we have this orange arrow coming out. So this is a workout, and this is QL. So remember what I said in the statement up at the top here? For any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. This is a little different. This is a single reservoir, but it's actually dumping heat into a reservoir. So let's look at this. This is a box that has two outs and no ins, right? So if I did the first law assessment here, I hate when I do that. And I say everything that's coming in, I put on the left. I got nothing coming in. Everything that's going out, I have two things coming out. So I have, what do I have? WorkNet plus QL. So I guess I have, what's my equation here? I have WorkNet is equal to minus QL. So that doesn't make any sense. I don't have energy balance here. I can't have negative. I can have negative heat loss, but I'm not a negative. It's already by the fact that I put it on the right hand side of the equation. It's already has a sign convention. So this doesn't make any sense. How come my work that comes out is equal to my heat that I throw out? It's actually negative to the heat I throw out because of the sign convention. So it's grabbing. So what's really saying, it's grabbing heat. It's negative of the heat that I already have coming out. So it's actually grabbing heat and throwing it into the condenser from the lake, and somehow that's generating electricity. Makes absolute no sense. So this violates the first law and the second law. Okay, it's a perpetual motion machine. If I would have done this correctly, if I would have said, well, I'm really putting heat from the outside somewhere, like from a burner or a gas burner, and I'm throwing heat out and I'm working, then I'm generating heat, then I'm doing the right thing, right? That's the traditional heat engine. Gets heat from a high source, throws it away in a low source, and produces work, right? QH. But I'm internally producing. So here's my dad, who passed away 7 years ago, I used to have an argument with him. Ever since when I was in college, he said, "Hey, son, check this out. I got this wheelchair, and it's an electric wheelchair, and it's and what I'm going to do is the motor in the wheelchair basically it produces a torque, right? It's a pretty powerful motor. So what I'm going to do is, instead of running off of the battery, I'm going to just what I'm going to do is just get some of that electricity from the generator and just funnel it back to the battery, and then and charge the battery, and then the battery charge will run the generator and the motor of the of the wheelchair, and I'll keep going forever. And of course I laughed, right? And and I didn't know how to explain it to him, but at the time I was a student. I don't think I even took thermal, but I said, "You're getting something for nothing, Dad." I said, "You have a wheelchair." I said, "Do you why even pay for electricity, right?" I said, "Just sit on a wheelchair and just, I mean, you'll have." I mean, I just said that doesn't make any sense. He said, "Well, tell me why it doesn't make sense." And then later on, he would always ask me to. He's like, "Hey, I know you're going to say no, but why? Why?" And then I told him, because it violates the laws of physics, right? I mean, we're not supposed to violate the laws of physics. So, it violates. You're violating the laws of physics, right, by doing that. And and I hate to be the person that I don't want to be a wet blanket, and rain on your parade, but but you can't get something for nothing, right? I mean, people talk about that all the time. On YouTube, right? You have places that are selling you, hey, I have this box, right? And you're gonna get a kilowatt, so you can power your house, and all it requires is you just put an initial, you need 10 watts from a battery, and then you run it, and it runs forever, right? And that's even like, you can just put the 10 watts in there, just crank it, and then it produces, and the government doesn't want you to know about this, because then the power plants are going to run out of business, and that kind of thing, right? And so this violates the laws of physics. This violates the first law right there, right? One kilowatt coming in, 10 kilowatts coming in, 10 watts coming in, 1 kilowatt coming out. So this violates so it can't happen, right? And so you know all right. So that is the perpetual machine. Excuse me. So I'm gonna stop there. This is where I stopped in the last class. Please, sorry, please look at the videos in chapter 6. Attempt the homework by looking at those videos. I haven't lectured on anything that can help you solve the homework, but I lectured on the key topics. Actually, I take that back. The heat engine that I talked about with that'll help you with the homework. But I haven't talked about coefficient of performance, and I haven't talked about Carnot. I'm gonna do that next meeting. All right. We're gonna get out early today by 15 minutes. Not even that early. Okay. All right. I'm gonna. You guys have anyone have any questions? I'll stick around if you guys have any questions, and we'll go into our office hour part of our segment here. Okay, I'm gonna stop recording.